In video 23 on the Foundations of the Computational Economics course, we take another look at NewtonRaphson Method, and in particular we'll look at the cases where Newton struggles and also have a multidimensional application, which is all very useful. So just to remind you, Newton method is an iterative solver for equations. The Newton step is defined by this condition here. We have to have the function calculated the previous approximation x and the derivative of the function and combine them in a particular way. You can go back to video number 13 to learn about the basics of the Newton method. And remember, we have mentioned many times that Newton is a very fast method compared to others. It has quadratic conversions, and that's what we really want to have in computational economic applications. And yet it's robust enough, or we can make it robust for our purposes. So today we will look at the potential problems of Newton method and at different things to be aware of, and we'll look at the multivariate version of it. So this is a code copied from video 13, which implements the Newton method. Again, you may want to go back to it, but just as a reminder, the main loop is here. If I comment out the main part of that loop, we are updating x's, and every time x0 is the previous iteration x, x1 is the next iteration, and we pass it back. You can see Newton step in line 7, and we are calculating the error as the distance between the two consecutive approximations. As you can see, this works on scalars. And break out of the loop if the error becomes less than tolerance. Now, if callback is given, then the callback function is the callback function call is performed for each iteration. We return. Oh, we should return x1 actually here. That's more like a Newton method. Okay. Let's look at this example here. Here's my f function. That's the example that we looked at before. G is the gradient of the x function, the derivative. And we can just call Newton like that. F, G, and the starting value. That's very important, as we will see. With maximum number of iterations 7, but we can, if there's not enough iterations, then there will be an error. The runtime error failed to converge in 2 iterations. All right, so that's for the code that implements the simple scalar Newton method. Now, I would like to make nice plots as always. So the standard header for getting ready to make the plots. NumPy is of course going to be used as well. Now, we will want to look at many different cases of running Newton method for different functions. And so I've written this function that wraps up the work, essentially, that we will be repeating over and over again. As you can see, the main arguments for the Newton method are here, but then also there are bounds for the picture and additional arguments that are passed into the Newton itself, so that we can change the tolerance level or the maximum number of iterations if we need to when calling this Newton pick function. This double star KW args, that's the way that Python allows for unspecified arguments, which are keyword arguments, KW, to be passed, and then I can just use all of them and pass them to some other function inside of this function. We'll see how it works. So what happens here? First, we make a grid over x of 1,000 point, plot the function in red, plot the 0 line in black. So we visualize the equation, and then we'll adjust the y limits of the plot. Let's not talk much about the plot step. We will see it will make sense at the actual pictures. and then we're trying to run Newton. But if there is a runtime error, so the convergence error as we just saw, then it simply prints fail to converge instead of producing an error that stops execution. Okay, and then we show the plot. So this is essentially just a visualization of the Newton method. I ran this cell, and we can go further. Let's now call this function. So we're going to call it with function f. The gradient is given by g, and we'll start at minus 2.5 and plot it between minus 3 and 0.5. Okay, here we are. Converged in 7 steps. And here's this intermediate plot that I didn't want to go through the code of. You can see that once we've plotted the zero line and the function that we want to, that gives the equation, right? We want to find the intersection of this function with the zero line. Here's our start, minus 2.5. Each iteration is printing essentially a vertical line to the function to show us where we are on the x. And then a part of the tangent line, as you remember, Newton makes steps in x by looking at by making a linear approximation of the function in question, the red line, at the current point. So the linear approximation is just a tangent, and where it crosses 0, that's our next iteration x. And so you can see that first iteration is this triangle, then second iteration is this one, and then we converge towards the solution here. In 7 steps, we've converged. Okay, so this is the visualization tool. Let's talk about when Newton fails. Well, first of all, if the equation has multiple solutions, then it is hard to say which solution we will converge to. And this is a fundamental property of Newton method, and this is something that we really need to be aware of. In economics, we meet that all the time, that unless we've proven a theoretical property of the function that we're working with, there might be multiple solutions. Be aware. Now, the particular failures of the Newton method include the following cases. Sometimes Newton diverges. And so there is something called a domain of attraction. These are all of the points in the domain of the function from which the Newton method would converge. That's by definition. So outside of domain of attraction, it either can diverge, go to infinity, or it may cycle. So cycles in Newton method are possible. We'll look at that. Now, the function domain can be limited, and that may present problems for Newton method because we have to calculate the function at each approximation while doing the iterations of the Newton method. Then we need to be able to calculate the function. Similarly, if the gradient of the function doesn't exist, then we get into the trouble of differentiability. And that's another thing to be aware of when applying Newton. Now, unfortunately, Newton can have really bad cases sometimes with reduced performance. But this is quite special, but we'll look at that. But I can tell you that in economics, I've never seen it happening. Okay, particular examples. Let's look at multiple solutions. We're using the same function actually, but now we will be plotting it a little bit farther out. You can see if the upper bound is 1.5, then there's actually 3 solutions. Well, of course, that's a cubic polynomial, if I remember correctly. Where's the function that we've looked at? And it is. It's x to the power of 3. So we should have expected 3 roots. And then there are. If we start from minus 2.5, then we find the first one. I've selected some nice starting points here to demonstrate that where you start from is really important. And let's not start from 2.5. X not equals. All right, there we go. Well, we might want to print this a little bit tighter. So here we are. So what happens here? We started from minus 5.95, which is here. And this is not far from this first root over here. But see, because this section this section here is quite flat, then we made a jump into a completely different part of the function and suddenly started converging onto a completely different root. And this is the one that we found here. Okay, now if we start from yet another point, and I guess I want to look a little bit wider, between -2 maybe. Here's another example. We started in between this point and this point, so these two roots, but again we were sort of taken away by the Newton method and then eventually converged to the initial root that we've seen. The point here is that with multiple solutions, the starting point may be taking you, or depending on where you start the Newton method, you will be finding different roots. And there's nothing really we can do about that. At least with Newton method, that's just the fact that it's hard to control and it can be very sensitive to different small changes of the initial point. Let me demonstrate. Point 47, we're still in that root. Well, let me take this one. So you can see we've converged here, but if I change it just a little bit, so to say 0.6, maybe 605, you can see where it's going. Oh, now we shoot away very, very far. Okay, and the number of steps also increases. Let's come back to this point in the example in the end of this video with the multi-dimensional case, where it will be very obvious that the starting point is extremely important. To over here we've converged to this root on the left right away. All right, what about diversion? Well, this is a different case. Now we are solving for the single root of the arctangent function, which is drawn here in red. The derivative is well defined, and let's look at these two cases. Right, in the first case, I've started it from 1.25, and as you can see, it nicely converged, sort of jumping between positive and negative values, but still nicely converged to the root, which is 0. But if you started from 0.5, what happens is that that's enough to throw Newton sort of away from the root, and then at each iteration you will just start sort of going around and around and around, and we fail to converge in 8 iterations, and we will fail to converge in 28 iterations just as well, except now that we are also getting into the problem of overflow, and that's because this iteration is now working with such huge numbers that do not fit into the float representation. Okay, divergence. What can we do here? Well, we have to talk about the region of attraction. As you can see, there is some region around the root here from which we will converge to the root. But if we start from the outside of the region of attraction, or domain of attraction of the Newton method, then it may diverge. Now, here's an interesting example with cycles. Look at this. This is still the initial function, the third degree polynomial, with a nice derivative. If I started in a very particular point, x0, and run Newton method, what happens is that it just runs in circles, and it failed to converge. Well, this is an example of a loop. And in this example, it was actually not easy to find this loop, but as you can see, it exists. It's not stable. Actually, small numerical errors accumulate, and if I let it run a little bit faster or a little bit longer, then it will eventually converge in 24 steps. But it starts very slowly because of this near loop near cycle condition. There are, on the other hand, cases where the cycles might be stable, and then Newton will just happily cycle over and over in the same direction. If you want to know how I found the starting value here, this negative 0.5689 and so forth, well, what I had to do is I had to run yet another Newton method, which found the solution such that two consecutive steps of Newton steps, this ns here codes up the Newton step with its own derivative, and then the f2 is the objective function for the equation that I want to solve. What is it? It's the application of an ns, the Newton step, once and twice, and I want to compare that with the point where I started with. So I want to solve the equation where we start from some point and after two steps arrive to the same point. Well, you have to calculate the gradient of this function to be able to apply Newton method, and then you just apply Newton method to a high degree of precision. And here is an interesting point. If you don't do it precisely enough, then let's do it to the 4th degree of precision. Fail to converge in 15 iterations. Am I doing everything right here? Oh yeah, there we go. So if the degree, if tolerance is not high enough, then the solver for the initial condition for looping is not accurate enough, and then we don't get any loop, right? So in order to get nice results, you really need to crank down that precision of the solver for the point from which the Newton method would cycle. Well, again, as you can see, this is a pretty special case, but this is not impossible. Newton may cycle. Now, let's talk about the function domain. What can happen here is that function may become undefined in some point of the space of X, and if Newton is unaware of that, then it will just run, or it may run into the area where the function is undefined, like a log, for example. And here we are. If we start log close enough, or close enough to the origin at lower values of x naught, then it nicely converges to the solution, which is 1, of course. But if you start too far, then the first step wants to go to the negative values. That's where the log is undefined, and the Newton will basically work with nonce and run for all of the iterations, having nonce all over the place, and never converge. And this can be a problem, a serious problem in economic applications, as we will see in the future video, one after the next one. Okay, now finally, there are special cases where Newton has strange performance. So look at this equation. This is x to the power of 9, and of course the power is odd, so there is a single root at 0, which is repeated. We have a nicely defined derivative, but if we try to run Newton iteration here, say starting from x naught of 1, what happens is that, well, the graph doesn't tell us much. What happens is that it takes 99 iterations, which is insanely slow. And as you can see, looking at the powers and the error term, there is nothing like quadratic convergence here. It's just, going slowly, -4, -5, -6, -7. We would, from Newton, we would expect this power in the error, the power of the negative power of 10th and the error term, to be doubling or approximately doubling every iteration. Well, yes, unfortunately, it could be that Newton performs poorly in exactly these situations where the function approaches the root in sort of very, very slowly, in a shallow manner. Well, the fortunate fact is that this situation in economics basically is very is very untypical. So I can confidently say that many of these problematic cases rarely happen in the economic applications. But some of them are very important. So, like I said, multiple solutions is one thing to be aware of all the time. The function domain constraints, that's annoying. You will know that something is not working if the method runs into the space of variables of parameters where the functions are not defined or the derivatives are not defined. And you will have to basically work around that, or maybe reformulate the problem, or maybe study the theoretical properties of the problem, which is always a good idea. Now, finally, domain of attraction. So we want to start Newton in the domain of attraction to ensure convergence and also fast convergence, as opposed to the fact of starting it outside and seeing it diverge. How do we deal with all of these problems which still remain? Well, multiple solutions is a theoretical property. So there's not much to do except for theoretically analyzing the model at hand and seeing whether there might be multiple solutions there. Numerically, you can try the approach that we will label Monte Carlo later in the course, where you basically start Newton from a bunch of different starting values and see whether they converge, all these runs, whether they converge to the same solution. And if they do, then you have some certainty, right? Some assurance that there's a single solution, but not a proof. But on the other hand, if you see Newton method converging to different solutions, then you definitely know they exist. You definitely know there's multiplicity. The same thing goes with domain constraints. It's basically studying the theoretical property of the model. Domain of attraction is more of an art. So again, trial and error, but a very good idea is to combine a few methods. So you can have a slow, robust solver in the beginning to get, with the main idea is to get into the domain of attraction of the problem. And then you can switch to a Newton method for fast convergence. And that's exactly how a classic estimation method called nested fixed point estimator in discrete choice dynamic models is designed. It's designed some time ago, but still remains one of the most powerful estimators for the dynamic discrete choice models. Okay, let's talk a little bit about Newton fractals. So this domain of attraction is kind of a mysterious thing. There can be heuristics, like in the NFXP estimator, of when it is good to switch to the Newton method after a robust first stage solver. But in general, it's hard to say or hard to characterize the domains of attraction, as demonstrated by this example. So look at the equation. It's a quite simple equation with x cubed. The solution in real numbers is, of course, just one, but there is also two solutions in complex numbers, and they are this shouldn't be here. Two symmetric solutions in the complex plane, actually. And so what's the exercise here? Well, let's solve this equation in complex plane by Newton method, which is possible. And for each initial point, for each possible x naught in the complex plane, we can draw it with a color which corresponds to the number of iterations that it takes Newton method to converge. But if it doesn't converge, we leave it white. And here's the picture. Here, the three solutions are drawn here. So the light green means that we converge in one iteration, and darker colors mean that we are converging in a larger number of iterations. And now you can see here these bands of the fractal structure. They are the points which are outside of the domain of attraction. And the fractals arise very naturally because, as we saw in the simple one-dimensional example, it could be that because of the shape of the function, Newton method is thrown into some completely different area of the space of the parameter space, which could happen to be in the domain of attraction. And so each domain of attraction has sort of a ghostly image from which you could reach the domain of attraction. And because of this recursion, then you have immediately you sort of fall into the fractal structure. Anyway, I recommend watching this video on building these fractals, which is pretty cool. Okay, let's look at the multivariate NewtonRaphson method. Well, it's essentially the same thing, but it can be formulated in matrices, in vectors, and work on the now systems of nonlinear equations rather than just one equation. And we'll look at the systems of n equations with n variables. So g of x is going to be an n-valued function. Okay, we take the derivatives of all of these subfunctions, right, element functions, with respect to all of the variables, and we get an n by n matrix, which is called a Jacobian matrix. And I denote it with this nabla symbol, like a gradient, but we remember that this is a matrix, actually. The Newton step looks the same, except now we have to do this matrix operations in a step. So we are dividing the vector of n elements with the matrix n by n. And that, of course, gives us the vector of n, and x is a vector of n, so xi plus 1 becomes a vector of n as well. So as you can see, the difference is really that now we have to compute the inverse of this gradient matrix, of the Jacobian matrix. And that's where Newton method is more complicated computationally than simpler methods. And this is basically the cost of being fast. So Newton method is fast, but requires the inversion of a potentially large matrix in here. All right. Now, where's this used? The classic application is optimization problems. So imagine that you have some f of x to be maximized, and f of x is a function of n variables. The first order conditions are then written as a system of nonlinear equations, where g of x can be thought as a gradient of x, right? This is a n-valued function because we are calculating n derivatives with respect to each variable of f. And so we have n equations of n variables, each of which has to be equal to 0. So this is the first order conditions in the multivariate optimization. And then, of course, we can do a Newton solver on this equation, except now we need to calculate the derivative of the gradient, right? So this is what's called a Hessian matrix, and it can be written like so. So the Newton becomes the optimizer, the method that solves the first order conditions for some invariant maximization problem. And this is a typical application for multidimensional Newton method. Although there can be other applications as well. So if you think about the product market equilibrium from the previous video, which was solved by successive approximations in the space of the utility functions, well, that could as well be solved as with the Newton method, multidimensional multivariate Newton method, after appropriately specifying the function that we want to solve for and its Jacobian. Let's look at this example. So imagine that we have a function of two variables f of x, y, and this is given by this quite complicated formula here, which I selected to make the the graphs and the example interesting. This is the function that we want to solve the first order conditions for. So let's write the first order conditions. Here they are. This is our function, and this is the gradient of the function, or Jacobian of the function, you could say. This function is not n-valued, right? So what we have is just a vector, the gradient of consisting of two elements. And then taking the second derivative, now we have to differentiate this g of x and y. And then we have the Hessian matrix of f or the Jacobian matrix of g, which is now a matrix 2 by 2. And you can check these calculations here, but I think they are fine. Now let's start coding this up. I'm going back to slides. And here's my f function. And because this is a function of two variables, we'll be looking at the contour plots. And here's a little, simple code to automate the creation of these contour plots. I sometimes want to plot them on a given axis, and then no new axis is created. Otherwise, it creates an axis and puts the contour plot here. What are important things? Well, we have a bound, and we will be drawing with 0 in the middle all the time. So the minus bound is going to be the area where the plot is created. The mesh grid is a special operator in NumPy, and it basically creates the grid points that are needed for drawing the three-dimensional plots or contour plots. And here's the call for the contour plots. Oh, we also control for the number of levels by specifying, at which level each contour plot needs to be drawn. And we're making the aspect ratio of the axis equal so that the units on x and y are the same, or they have the same length. And so here's our f function. If we just plot it with default in the default region, which is from -1 to 1, what we see is this top picture here. And it's a nice looking concave, probably. The yellow ones are higher, right? Function that we want to optimize, so we want to find a point here. But as we zoom out, actually what it is that we have this quite complicated shape. Let me redraw this here. So you can see that there's a hill here surrounded by some valleys, some depression around it. And you can see there are some more hills. And so if I plot it on even a larger scale, well, you can see there are a lot of hills. Essentially, this is like an egg carton. The hills and valleys come in sequences and cover this huge space. All you see is this valleys and hills. And I guess that's what you would expect from a function that has lots of trigonometric functions in it. It will be repeated in all directions. Okay, well, that means that, we are having here an extremely hard optimization case, right? All of these hills are of the same height, and each of them is a local optimum, local maximum that we may end up in. And moreover, you can see that when we solve for the first order conditions, any of the flat points is a solution, is a critical point. So the set of critical points is very large. You may end up at the top of the hill, you may end up in the bottom of this valley, and you could also end up in a saddle. Points around here and here. This is where the function is also flat. Okay, now I've coded up the gradient of f and the Hessian of f, the Jacobian of g, as just lists of function, or it's a lambda function of two variables that returns a list. That's what it is, right? So it's a lambda function of x and y, and it returns, two numbers. One is here, and another one is here, and they're just combined into a list. That's what it is. And here it's a double list. It's a list of lists because of this double brackets. And of course, you can already see that this will be easy to convert to NumPy arrays later, because we want to do matrix operations on them. Some more plots. I've created two axes here with the subplots command from matplotlib. And into the first axis, I'm going to plot the gradient as a function of x, y. But see here, I'm only taking the first element of that list, which we just looked at. And so this is going to be a derivative with respect to x, whereas the second plot shows the derivative with respect to y. Now, both of these functions, both of these partial derivatives are functions of two variables, and therefore we need to plot them over the plane as well. And you can see that they have different shape, but also, as expected, they have this pattern of repeated hills and valleys. Now we can do the same for the Hessian. And here it's going to be a second derivative, so a matrix, and we can draw it as a matrix of plots using, again, the subplots command in the matplotlib. And this is the second derivative with respect to x and, again, x, with respect to x and y, and second derivative with respect to y twice in the corner here. Okay, so all these plots is just to show how complicated the problem actually is. So we are working with many different functions, each of which is a function of two variables. Okay, we need to modify our Newton method code slightly. The arguments are all the same, but here are two additional lines. So when an x naught comes in, this is going to be a vector, right, of some sort, probably a NumPy array. But the functions, as we define them, they expect two different arguments, x and y. And so therefore, I'm going to unpack the array here and call the function with explicit first and second argument. Same thing for the gradient, first and second argument. And then the function will return a list, and we want to convert this list into NumPy arrays right away. And well, the way this is going to be done here is that I define this lambda functions, which is a conversion, as I described, into the NumPy arrays, and we can call them with the axis. Then the main loop is pretty much the same, except now the error that is calculated needs to account for the fact that x might be a vector, and so we need the NumPy version of the absolute value and the Amax to take the maximum over the deviations of each of the components. Oh, and of course, the Newton method, that's the main change, of course, has changed, because now we cannot just divide by the value of the gradient. We need to take the inverse matrix, the inverse of the matrix of the NP gradient, which is returned here, and then matrix multiply it by the vector which is returned as a function value. Okay, so this is essentially this would essentially work for any dimensions, but because we are unpacking explicitly the vector into x and y, this is called Newton 2, which is supposed to refer to the two-dimensional solver. Oh, and again, this is not correct. This should be just returning the last iteration. Okay, so let me skip the this plot step function. We will see on the output exactly what it does, and start calling the solver. And so it's here. X is an array, right? So we have to give it a starting point as an array of of two things. Oh, I guess I have to go back to see the plot. Oh, this is a little bit troublesome. Let's copy all of this code into the previous cell here and run it this way. Okay, that's how it's going to work. So here's my plotting function, and I'm initializing at the point minus 1.8 minus 0.2, and then I'm running the Newton, the two-dimensional Newton, and reporting whether it converged and how many steps and what's the found optimal point. Now the g of x star should be 0, right? The g function is the one that we are solving as an equation. And you can see here that the complicated plot step essentially adds a path that the Newton method takes in the two-dimensional plane. The dot marks the initial value, and you can verify that by looking at this initial value minus 1.8, which is somewhere here, and minus 0.2, which is a little bit below 0. And you can see how Newton method really jumps around in this place and then settles onto the flat spot in the valley, unfortunately, over here, and really solves the first order conditions. So this is really a flat spot, but you can see how it bounces around in the beginning quite a lot. And so that means that we are not starting in the domain of attraction of this particular solution that we found. Let's try another run. And so here we're starting at the slope and jumping away quite far to come back and settle actually in 8 steps, but we settle in the settle point. So here is the settle point where Newton stops. Interesting. But again, you can see that the equation is solved quite accurately. Another try. Oh, and here we have to even redraw the picture. It jumps very far away and then settles over here. A few more runs. Again, jumps quite far away. And even further away. So essentially, it's like a randomization device. We start somewhere, and the starting points don't differ all that much, but the results differ quite a lot because of this complicated structure, this egg carton shape of the function. We tend to bounce around with Newton method quite a lot. But even with this sort of silly example, you can see how two-dimensional Newton method is able to find the flat spot of the egg carton and solve the first order conditions quite efficiently in a relatively small number of iterations. And another thing to note is, this is not a very simple problem just in terms of sort of writing down the derivatives and second derivatives of the function that we're interested in. Okay, that's all for this video. Oscar Velets has produced a very nice series of videos which explain various optimization methods, actually. But in particular, on Newton method, there's 1, 2, 3 really nice videos that I recommend watching. And then if you want to learn more about the NFXP estimator, there's a nice Wikipedia section on it. Okay, see you next time.